Horizon Telescope, we all caught an awe-inspiring glimpse of the first true image of a black hole. And since that moment, this historic discovery has continued to inspire scientists to ask more questions and to look. Thanks to the incredible efforts of the Event Horizon Telescope, we all caught an awe-inspiring glimpse of the first true image of a black hole. And since that moment, this historic discovery has continued to inspire scientists to ask more questions and to look for even more answers throughout our universe. The Event Horizon Telescope has continued to push the frontiers of science and discovery. And today, because of the incredible work of all those involved, I am honored to join you as we announce another exciting and historic breakthrough.
At its heart, towards the constellation Sagittarius, is Sagittarius A Star, the supermassive black hole suspected to reside there. A source that has been a focus of intense astronomical studies for decades. Observations of stars orbiting around it revealed the presence of an object that is very massive, 4 million times the mass of our sun, but also very faint. For me personally, I met it 20 years ago and have loved it and tried to understand it since. But until now, we didn't have the direct picture confirming that Sag A Star was indeed a black hole. Today, the Event Horizon Telescope is delighted to share with you the first direct image of the gentle giant in the center of our galaxy, Sagittarius A Star. This image shows a bright ring surrounding the darkness, the telltale sign of the shadow of the black hole. Light escaping from the hot gas swirling around the black hole appears to us as the bright ring. Light that is too close to the black hole, close enough to be swallowed by it, eventually crosses its horizon and leaves behind just a dark void in the center. Getting to this image wasn't an easy journey. It was one of getting and processing petabytes of data collected from those telescopes, of imaging algorithms more complex than many that have ever been developed. What made it extra challenging was the dynamic environment of Sag A Star, a source that burbled and gurgled as we looked at it. And the challenges of looking not only through our own atmosphere, but also through the gas clouds in the disk of our galaxy towards the center. In 2019, we revealed the very first such image, that of the supermassive black hole in the M87 galaxy. That black hole is 1,500 times more massive, making its horizon 1,500 times larger. But it is also 2,000 times further away from us. This makes the two images appear very similar to us when we gaze at them in the sky. But the two black holes couldn't have been different from each other in practically every other way. The one in M87 is accumulating matter at a significantly faster rate than Sag A Star. But perhaps more importantly, the one in M87 launches a powerful jet that extends as far as the edge of that galaxy. Our black hole does not. And yet, when we look at the heart of each black hole, we find a bright ring surrounding the black hole shadow. Now we know that it wasn't a coincidence. It wasn't some aspect of the environment that happened to look like the ring that we expected to see. We now know that in both cases, what we see is the heart of the black hole, the point of no return. These two images look similar, because they are the consequence of fundamental forces of gravity. Space-time, the fabric of the universe, warps around black holes in exactly the same way, regardless of their mass or what surrounds them. This is what we had hoped to find, given the predictions of Einstein's theory of general relativity. And it is exactly because of this fact that we are able to use these new observations, the image of Sagittarius A Star, to perform one of the strongest tests of general relativity to date. That allowed us to make a prediction for how big the image and the black hole shadow should be. Now we have two laboratories in the sky, M87 and Sagittarius A Star, for exquisite tests of extreme environments.
To distinguish the ring-like structure in Sagittarius A Star, our telescope had to be almost as big as the Earth. Fortunately, the technique of interferometry allows us to link pairs of telescopes that are very far apart into the equivalent of a planet-sized telescope. We use this technique both for Sagittarius A Star and the black hole in M87, or M87 star as it's called. But these two black holes are quite different from each other, as Ferial described, and for reasons Katie and Michael will explain, imaging Sagittarius A Star turns out to be a lot harder. Today's results come from the same 2017 observing run as M87 star, but with a big difference. The South Pole Telescope at NSF's Amundsen-Scott South Pole Station observed Sagittarius A Star, whereas M87 star was completely out of view. So while we had 7 telescopes to see M87 star, all 8 could see Sagittarius A Star. The South Pole Telescope is perfectly suited to observe Sagittarius A Star, both because it can see it continuously and because it significantly increases the resolution of the array. In interferometry, each radio telescope is at a different location. By correlating their signals and studying resulting data, we can reconstruct images of the source. The more telescopes, the better. The farther apart they are, the more we can zoom in on the source. Turning pairs of telescopes into the nodes of an interferometer is a process similar to everyone shaking hands with everyone else in a room. You need at least 2 people, and the number of handshakes grows very quickly as you add more people to the group. So the amount of data we get also grows very quickly with each telescope we add to the EHT. When we observed Sagittarius A Star, 8 telescopes collected around 3.5 petabytes of data. That's equivalent to about 100 million TikTok videos. But just gathering the data isn't enough. The data has to be carefully combined, calibrated, and converted into an image, with teams of scientists, many of them right here in this room, working on each stage of the process, where supercomputers combine the signals and produce raw input data. The calibration team combines the raw data with information about the sensitivity of each telescope to form the data used by the imaging teams. And then the imaging teams process the information using a variety of methods to reconstruct the best possible images of the hot plasma surrounding the black hole. But Sagittarius A Star brought a number of new specific challenges, even though it is closer to Earth. First, M87 star doesn't change very quickly, but Sagittarius A Star does. In this sequence of model images, 1 second is equivalent to almost 2 days. Imaging a rapidly spinning turbulent source like Sagittarius A Star is a lot harder than it was for M87 star. As Katie will describe, material swirls around M87 star over the course of many days, but it takes only a few minutes for material to move around close to the horizon of Sagittarius A Star because it is much smaller. It changes quickly, so we had to collect our data quickly. To further complicate things, we see Sagittarius A Star through an enormous amount of material in our own galaxy, which scatters the radio waves and blurs the image. But years of observations at other wavelengths have made it possible for astronomers to partially mitigate the effects of this blurring. The result is an image that, until we finished our analyses, we were never sure we could get.
This image from the Event Horizon Telescope required more than just snapping a photo from telescopes at high mountaintops. It is the product of both technically challenging telescope observations and innovative computational algorithms. To understand why, let's go back to how our telescope works. As Vincent mentioned, the EHT doesn't work like a regular telescope. Instead, our radio telescope shakes hands. They work in pairs, with each pair contributing a little bit of information to the entire image. Telescopes that are far apart can detect the smallest, sharpest features of the image. Orientation is also important, with each angle picking up different parts of the whole. Telescopes that are closer together become sensitive to the broad features of the image that the wider pairs can't see. And combined, these components of the image can provide a good representation for the target we're observing. Luckily, as Earth rotates, the projected separations and orientations between the telescopes change, providing more, but not all of the information we need to make a perfect picture. As Michael likes to say, taking a picture with the EHT is a bit like listening to a song being played on a piano that has a lot of missing keys. Since we don't know when the missing keys should be hit, there's an endless number of possible tunes that could be playing. Nonetheless, with enough functioning keys, our brains can often fill in the gaps to recognize the song correctly. The hot gas spiraling around these two black holes moves at roughly the same speed. But where gas takes days to weeks to orbit the much larger M87 star, for Sagittarius A Star, because it's a lot smaller, gas can make a full orbit around its event horizon in mere minutes. And that means as we were collecting data during the Earth's rotation, the material was swirling around Sagittarius A Star so quickly that Sagittarius A Star's appearance could change from minute to minute. To capture the range of potential Sagittarius A Star appearances, our team produced tens of thousands of different images with different methods that filled that information in differently. Each of these images is slightly different, but they are all consistent with the EHT data. By averaging these images together, we're able to emphasize the common features appearing in most of them, and here a bright ring clearly pops out. But it's important to note that not all the images that we recovered looked alike. In fact, we found that we could cluster the recovered images into 4 categories based on similar visual features. 3 of the clusters contained a ring-like feature with only differing brightness around the ring. However, there existed a much smaller 4th cluster that contained a variety of images that did not appear ring-like.
We are peering into a new environment, the curved spacetime near a supermassive black hole. And it is teeming with activity, always burbling with turbulent energy and occasionally erupting into bright flares of emission. So we developed tools that locked in on the bright rings in all those images that Katie showed and measured their properties. We also developed a set of simple models that we could fit directly to the EHT data. So in the first way, we divided our data up in time, and then we fit a series of nearly instantaneous snapshots. This ensures that our measurements aren't being contaminated by the variability of Sagittarius A Star. And we then combine all of those snapshots into a single average model. In the second way, we fit a model to all the data at once. Here we're fitting for the average image structure, along with an extra source of variability noise that's sitting on top of that average. And this procedure is very similar to what we did to make the images. By combining all of these different approaches, we were able to precisely characterize the properties of the ring. And we found that we can measure the ring diameter to an accuracy of about 5%. So the blue ring that you see here is the predicted shadow diameter from the stars, and that band is showing the range of possible values. Most of the uncertainty here is actually because we don't know whether or not the black hole is spinning, and the spin has a small effect on the shadow diameter. Next, we wanted to study the turbulent environment around the black hole. So we turned to supercomputers. A large team across the EHT, including many people here in this room, created a whole zoo of numerical simulations of black holes. These let us see mock movies of what a perfect instrument might observe for Sagittarius A Star. With these simulations, we can move to any viewing location around the black hole. We can look at the black hole edge-on, as you see here, peering through the disk of material that's flowing onto the black hole. Or we can tilt our camera at any other inclination and view the black hole face-on from above. We can also vary the properties of the black hole itself, allowing it to sit still or spinning it up to a maximum rotation set by the speed of light. And we can also vary the properties of the magnetic fields and the gas near the black hole, simulating weak and turbulent magnetic fields or strong and dynamically significant fields. So we're left with only a handful of simulations that can describe nearly all the features that we observe. And these simulations reveal an absolutely remarkable environment. First, we see that only a trickle of material is actually making it all the way to the black hole. If Sagittarius A Star were a person, it would consume a single grain of rice every 1,000,000 years. And while some black holes can be remarkably efficient at converting gravitational energy into light, Sag A Star traps nearly all of this energy. Only 1 part in 1,000 is converted into light. M87 was exciting because it was extraordinary. Sag A Star is exciting because it's common. So this is driving us to making even better measurements and sharper images. And the first challenge we need to overcome is the scattering. So even with a perfect instrument at 230 gigahertz, this is the kind of image that we would see on the sky. This image is fuzzy because of the effect that Vincent mentioned. We're looking at Sag A Star through the arms of the Milky Way, and this is kind of like peering at it through frosted glass. Because of the scattering, the crucial image details, such as the sharp ring that comes from light that's bent all the way around the back of the black hole, are lost. But with support from the National Science Foundation and other partners, we are already pushing our instrument further and going to even more challenging observations at 345 gigahertz. These will cut the effects of scattering in half, producing much sharper images. And we're not stopping there. We are already designing a next-generation instrument, adding many new telescopes around the world to the EHT. And this improvement will help us move from these still images to capturing the first high-resolution movies of black holes, letting us witness them in action and continuing this quest toward the boundary of the unknown.